All right. So as I said, basic electronics introduction for the non-technical. And this is a primer course for people taking their tech or general who either haven't gotten the exposure to basic electricity or would like a refresher. And it's based on a whole bunch of whiteboard sessions that I've done over time for various non-technical people, giving them an introduction to electricity. So we're going to talk about what electricity is, how electricity flows, which is very contrary to what people think. Where does electricity flow? Something to think about, especially when you're trying to design a safe station. How do we measure electricity? A little bit of the math, nothing complicated, and then some basics on series parallel circuits. If you can grasp this, you can grasp a lot of more complex topics because they have parallels to this. Parallels and parallel circuits. That's a bad pun. So anyway, that's what we're after here. So first thing I want to talk about is what is electricity, okay? Um, electrons, protons, neutrons, all that kind of stuff. And by the way, no one cares about neutrons. No one, they don't do anything. They just sit there and look good. So electricity, it's really a set of physical phenomena associated with the presence and potential movement of electrons where differences in charge exist. That's the fancy term, okay? Opposites attract, remember that one? Likes repel. Well, when you charge a battery, you're accumulating an excessive charge on one plate, negative charge, and it'll just sit there, fat, dumb, and happy, just kind of vibrating around until you get a circuit path. And then when there's the ability for electrons to flow, they're going to go zooming out looking for that positive charge. The opposites attract. So that's exactly what you need to think about when you think of a battery or any electrical source, okay? AC is just DC dancing back and forth. It's that simple, and it gets bizarrely complex if you dig deeper than that, okay? So if you think about a battery and you think about water, because the two common analogies that I've used that seem to make sense to people are how water flows through pipes and how traffic flows down a highway. I did a lot of water illustrations in here because they're easier. I tried to do some traffic illustrations and they were messy. But if you think about a battery, you've got the negative charge here, and that is very similar to having a stored amount of energy at the top of some hydroelectric device or a dam or water storage device, okay? The positive is that which draws the charge down. And in this case, the water, it's gravity. Now I have a nondescript device at the bottom of that pipe. That could be a pump, a turbine of some kind, whatever. In your electric circuit, that's going to be your light bulb, your diode, your switch, your whatever thing that the electricity is going to run, okay? So think about this. If you've got electricity and it's going to flow, just like the water, we refer in the water to opening a valve. On a circuit, we close the switch. Same difference, okay? So the valve opens, the water flows. It's that simple, okay? Close the switch, the same thing happens, okay? And just like the water at the top of the reservoir drains down to where there's not enough water to drain anymore and fills up at the bottom, the battery does the same thing. There's a lot of nuance and complexity to it, but it is in effect, for your purposes, trying to understand electrical flow, that simple, okay? Where does electricity flow? So again, we're going to do some pipes and hoses kind of stuff here. You can use highways, you can use roads. It needs a path of some kind. So electricity will flow through solids, copper wire, human flesh, any number of things. It'll flow through liquids. And think about the famous scene of the guy standing on the wet floor when the wire hits the ground. It'll flow right through liquids very easily. And it flows through gases, and it flows through gases fairly dramatically, and that's what you're seeing in lightning, okay? So electricity can flow through almost anything. There are materials that are considered insulators that it won't flow through, but given enough potential energy, it'll either arc past it or it'll make it conduct. And you'll see that used to our advantage in devices that are sort of conductive, but not really. semiconductors, diodes and transistors that we've talked about a little bit, and we'll talk about more in the session that Bill's going to run. Okay, so electricity is lazy. Keep this in mind. And this is why grounding is important. You want to get things like lightning to go where you want it to go. So when lightning hits, it's going to take the shortest, laziest path to get to ground. Ground in this case is the ground, but ground is it's that side of the battery that it wants to get to, kind of thing. So if there's a better path, guess where the electricity is going to go? And if you present a better path, guess where the electricity is going to go? And it's the case all the way around. So no matter what you do, electricity is lazy. Unfortunately, it's also lethal. So bear that in mind. So when you have a basic circuit, question time, how fast does electricity flow? What's the standard answer?
Speed of light.
Speed of light. Close the switch, bulb comes on. Okay. Now what's interesting is how electricity flows, not what people think. A lot of people have this as an understanding of what electricity does. Okay. And that's why they think that it takes a certain amount of time for the bulb to come on, because the electricity is flowing in a conga line, if you will. Okay. The truth of the matter is it doesn't flow that way. Some people think it flows like this. You just bump the electrons over. So that you've got a pipe full of water, you push water in one end and water comes out the other end. And you think that's how electricity flows. I will tell you, unfortunately, I didn't have time to finish this illustration, because how electricity really flows is very different than this. When you close this switch, yes, all these electrons in this wire, they're just sitting there dancing around randomly, and then the charge causes them to slowly migrate around. Slowly is a relative term because they go really fast, but energy actually flows. If you were to look at it, you'd see energy emanating out of the battery from both sides, and it would be emanating across to the bulb. And that's the weird concept that people don't get. Okay, and we'll talk about that more later, but just understand that we talk about electron flow and there's some validity to that, but it is more complicated than that. But still, the circuit works just like we talked about. Close the switch, bulb comes on. Okay, so let's talk for a moment before we get into the math about how we measure electricity. Okay, we're going to measure the force that electricity exerts, or voltage. We're going to measure the flow rate of electricity. We're going to measure the resistance or opposition to flow of electricity and the resulting power that that creates. Okay, so the first thing we look at is voltage. Water tank. Think about the old town water tank. Okay, if you live down at the bottom of the hill in town, you've got phenomenal water pressure because you're way below the town water tank. If you live at the top of the hill, you've got okay water pressure. The column of water has weight, that's pressure, and that's how you need to think of voltage. So you see, I've got an illustration here of a very high water tank, and that's going to be high pressure or high voltage. A low water tank, low pressure or low voltage. So when you think about electricity in terms of voltage, that's the pressure. The fancy term, electromotive force. The unit of measure, voltage, the symbol E. And this is where some people get tripped up. Why E? Okay, well, in this case, it's a little obvious. Why the E? It's because of electromotive force, okay? Memory device for you. Electromotive force, why voltage? It's the way I tell people to remember is overpronounce electromotive force and you get voltage, okay? Electromotive force is voltage, is E. That's about the best memory device I've got for that one, okay? But again, it's the pressure. Think about a column of water and you push on that pipe. You blow in the end of that pipe or you push water into that pipe as hard as you can. The harder you push the water, the higher the pressure, the higher the voltage, okay? So that's one way that we look at electricity and measure it, the pressure or force, the electromotive force. The next thing we look at is current, and that is the rate of flow. How much water flows through the pipe in a given moment in time. So it's how fast the charge flows. Electrical charge is measured in coulombs. It's a unit of measure that Charles Augustin de Coulomb came up with, and nobody remembers him. If you're an engineer, you know coulombs. If you're not, you don't care. So instead, we measure the flow of electricity in what's his name's units per time. So, and we call that amperes or amps. Okay. So here we go again. Current. Everyone would say, gee, let's use the symbol C for current or A for amps. But no. Why I? Anybody want to take a guess?
Sounds like an awful intense subject to me.
Yeah, well, blame the French. Intensity de current. Current intensity. That's why we use I. So
I
if
see
you
what
want
you
to
did
remember that
there.
one, blame the French. Okay. And I can say that because I'm a Frenchman. All right. So we've talked about voltage or pressure. We've talked about flow, how much water flows through the pipe at what pressure. Now, usually to have some amount of pressure, you have to have something opposing it. Because if there was no opposition, the water would just zip right through. There'd be almost no pressure. And that opposition is resistance. Okay. Think about resistance as a constriction in the pipe. It causes opposition to the flow. The more opposition, the higher the pressure on one side of it, the lower the pressure on the other. And we'll talk about that more in a moment. So the unit of measure for resistance is the ohm, a Greek ohm or omega. The symbol is that Greek letter, okay? Now, I have to apologize in advance for this memory device. You will remember this because you will hate this because it will ring in your head, okay? This is how to remember it. Oh my, what big resistors you have, Granny. Yep. That's it. That's it. Oh
All
my.
right. Okay, Tom.
Yep.
What is an ohm? It's the same as an Englishman's house.
Yeah, exactly. I like mine better, Paul. But again,
I did that just to hear Judy's laugh.
now again, keep in mind we have the three major ways. There's a bunch of different measurements for electricity, but these are the three you're going to use for most everything. Okay, the pressure, the flow, and the resistance to the flow. Okay, voltage, current, and resistance. And we're going to put all this together in a couple of circuits shortly. Okay, but ultimately that results in power. We all know everyone wants the power. Now, power is measured in watts. And surprisingly, we screwed up here and we made the symbol W. So this one's easy to remember. And if you remember the inventor of the steam engine, you'll remember why. Good old James Watt. It's easier to understand what this means if we do a little bit of math first, okay? So yeah, I know what this means. It's bad. It's all me. So we're going to talk about a little bit of math now, and then we'll keep this fairly basic, and we'll do some simple devices to remember the math, okay? So first thing is two formulas, and there's a lot more formulas, but if you remember these two, you can figure out most anything, okay? E equals I times R, and P equals I times E. I remember these because I call them ear pie. Okay. Ohm's law and the power formula. You use these two formulas and you can determine all the basic characteristics of a circuit. Okay. So let's talk about the first one, Ohm's law. E equals I times R, pretty straightforward. If you want to know what E is, okay, Alan Paul, since you're our two victims, guinea pigs, test subjects, E, what is it? Anybody? Come on. We talked about three different measurements. Which one is E?
Voltage.
Voltage. Bingo. Electromotive force. Voltage. All right.
That took a long time for me to remember.
Yes, and that's why I did that. Okay. So it's real simple. Just like the formula says, if you know E and you want to solve for it, it's I times R. That's easy. Okay. The little circle chart here is a real handy thing to remember. Okay. E equals I times R. Real simple. Okay. Now, what if you don't know E, but you have, or you do know E, but you're missing I or R? So let's solve for I. I is what?
Carry.
Blame the French. Okay. So if you want to solve for I, look at the circle chart, the pi again, and look at that. I equals E divided by R. If you remember your good old days of solving equations, if you did that in school, you do the same thing to both sides of the equation. You want to solve for I, you got to get rid of R. So you divide that side by R. You got to do the same on the other side of the equals, because just like the equal says, both sides of the equation are balanced, they equal. So you divide by E over there. Divide by R rather. Cross out the R's and guess what you get? I equals E over R. Okay, the same holds true if you want to solve for R. Okay, you want to solve for R, look at the circle chart again. It's E divided by I. The advanced student will try this trick and say, let's solve for R. So we divide this side by I, we divide this side by I. That makes the I's on this side cancel out, and you get R equals E times E divided by I rather. So hopefully that makes sense, because we're going to do that all over again. The names are going to be changed to protect the innocent, but guess what we're going to do with the other formula? Power formula. P equals I times E. Again, if you want to solve for P, P is what?
Power.
Power measured in
Watts.
watts. Good old James Watt. Okay,
What'd you say?
what'd you say? P equals, there you go, I times E. Okay, simple enough. Now, if we want to solve for I, if we know I, Al, what are we going to do for I before I change the screen? If I'm going to, how do we solve for I? What's the formula going to be? You picking up
Well,
on
you're
this?
gonna divide E into P.
Exactly. So I is P divided by E, okay? And again, the fancy math person says, let's solve for it over here. Cancel out the E's, ta-da! I equals P divided by E. And similarly, if you want to solve for E, it's P divided by I. So we went through the same drill with two different formulas, but if you remember, the two formulas are real easy to remember. Just spell really bad and say ear pie, and you've got both formulas, okay? But there's the solution right there. So if we put both of these formulas together and we do all the fancy voodoo math, we come up with this. It's a great little chart to keep in a book on your desk if you're going to do any projects. But not everyone likes this. It's not easy to remember. But all the formulas are there, and if you solve for them, you can get to this. I take a much simpler shortcut route, just like I said. Ear pie. If you can remember ear pie, you can do it all. If you know at least two of these values, you can solve for all the rest. So if you know E and I, or if you know I and R, or if you know R and P, you can solve for all the rest. And like I said, that's an ear pie, okay?
Hey, Tom,
Oh, my.
Tom,
Yes,
Just
go
killed by
back a
the
slide,
third.
please.
what's that?
Go back a slide, please.
Okay,
There you go.
and
Here you go, folks.
oh, you sending it out? Okay, good.
No, I'm not
You
gonna
can
say, I've
document
sent
it.
it out. Everybody take a picture.
Yeah, and you
Great
can find
thing to
these
have on
online.
your phone.
There's tons of these online, and they're handy. They're real handy because you can solve everything for them. But if you don't, like I say, you can go this route and do ear pie, and it's easy to remember. Okay, so
That's gross.
But you'll remember it.
You spoiled
Okay.
dessert.
Yeah, you will remember it. So let me see here if I can get my pen working. My pen doesn't want to work tonight. It was working right before. Ah, there it is. I got my pen back. Here we go. So if I have a circuit, and this is going to be real tough because I'm not good with this, and I have a hand tremor. So drawing circuits is not easy. There's my battery. Got it out. Here's my circuit. Okay. I'm going to throw a good old fashioned light bulb in the circuit. A good old incandescent bulb. positive side of the battery, negative side of the battery, and here's my light bulb. Now, light bulbs all have a certain amount of resistance in the filament. That's how they work. And you overheat them and they glow, okay? So we've got a 12-volt battery, and we've got a 60-watt light bulb, okay? So now I have two of my values out of EarPi. So I've got E, remember EarPi, E, I, and R, right? And then you've got, whoop, R, and then you've got P over here. I won't repeat the I and the E, but I could, okay? Which values do we know out of this? Where am I putting my two values that I know? Where's the 12 go? Under what?
E,
E, so 12, right? Where's the P gonna, where's the 60 go? Under P, right, for power? All right. So how do we now solve for I and R? You remember the two formulas?
you would divide
E equals what?
I times R.
Bingo, you got it, okay. Times R. And what's our other formula? E,
P is equal to,
EarPi,
right there.
I times E. Now, in this case, what if I want to solve for resistance? Now, again, there are shorter ways to do this. Go back to that wheel. They'll give you a formula that'll solve for resistance easily. But if you don't remember all those formulas, remember these two, because you have your 12 right here and you have your 60 right here. So how do we solve? Do you remember that? You either can either memorize it from that pie chart, or you do this. You want to solve for I, you divide by E over here, you divide by E over here, okay? That cancels out. So I equals P divided by E equals what divided by what? What are our numbers?
60 divided by 12.
60 divided by 12, which equals what?
5.
5. So we now know there are 5 watts in this circuit.
Amps.
5 amps, bingo, current amps. So you got 5 amps flowing in this circuit, okay? Now, guess what you just did? You set yourself up to know what the resistance of that bulb is. Because if I have 12 volts and I have 5 amps, I've got my E equals I times R. So let's do that down here. Let's take E, I times R, remember? So what am I going to divide by over here to change this formula around to solve for R?
R.
Okay. I'm actually going to divide by I.
I.
Okay. I want to leave R by itself here. Okay. Divide both sides.
You got
There you go. So it's R equals E divided by I, which equals what divided by what? What are our values? What's our E? Al? E is voltage, right?
12 volts.
12? Yep. What's our current? We just figured it out.
5 amps.
5 amps. So what's our resistance?
2.2 something. 5 going to 12.
Anybody got a calculator handy?
5 going to 12 2 times, so it's 2.5.
2.4.
You'll get 2.4.
Now, what's the symbol?
We solving for resistance, so it'd be ohms, right?
Ohms. Oh my granny, what big resistors you have. Okay. Yes, I know it's bad and it's supposed to be bad. That's how you remember it. All right. So That is everything we need to know right there. Hang on, where's my eraser?
Oh no, I lost this eraser.
I lost my eraser. I know it's here. Screen. Pointers. Erase entire screen. There we go. And we'll put the projection screen up again and we'll move on. Okay. So now we have everything we need to know to figure out what's going to go on with this circuit. So pay no attention to that resistance value on the far side for a moment. We're going to go back to this and figure this out. I've got a circuit now that's got 120 volts and 15 amps. I can solve for that using the formulas and figure out the 1800 watts. It's real simple. Pi, P equals I times E. Never forget ear pi. 120 volts, 15 amps, 1800 watts. Okay. Here's the wife's blow dryer. All right. So now we're going to down the voltage. I'm going to take the voltage down to 75 volts. What do you think is going to happen to the wattage? What do you think, Al?
I'm waiting for the exciting conclusion.
Okay, here it is. Wattage goes down. Why did the wattage go down? Think of your formula. Remember, it was 120 times 15, so it was 1800 watts. Now it's 75 times 15. So it has to go down. The lower the voltage or the current, the lower the wattage. Okay? So let's put the circuit back where it was. And now we're going to change the current. What do you think will happen? What's ear pi tell us? What's pi, P equals I times E tell us is going to happen if I down the current?
I have to work that out.
Yep. Yeah, and that's exactly it, Paul. As you get used to it, play with the formulas. Again, 120 volts. We had 15 amps before, so it was 1800 watts. Now 120 volts, 10 amps, 1200 watts. Is that, even if you didn't remember which formula or how to do it at first, does that make sense to you? That if you drop down either side of a multiplier, it's going to drop down the result. Okay. Now here's where it gets a little more interesting. We'll put the circuit back where it was again. Now we're going to play with that resistance value. So I'm going to take that from 8 ohms up to 24 ohms. Now, what do you think is going to happen to the wattage? Best guess, up or down?
Down.
Okay. Al, up or down? Not sure?
Okay, pi.
No,
Okay, that's all right. That's all right. Now,
Okay.
again, we're going to go back to that basic math. First, we're going to look at the complicated math because, yes, it goes down. Okay. Now, think about this like a water pipe. What I did is I just put a constriction here in the water pipe. So what's going to happen to the amount of power that you can get out of that if that were a pump or a turbine or something? You constrict it, you're going to get less power out of it, aren't you? If you take the hose and you're washing down the driveway and you squeeze the hose down, are you going to be able to be more effective washing the driveway or less effective washing the driveway? Resistance is going to constrict the pipe and reduce the water flow. Okay. So here's the fancy math from that big wheel. Okay. P equals V squared divided by R. And I've been an engineer for 40 something years. I don't bother with V squared R because faster than I can do V squared R, I do ear pi. Okay. So I'm going to take this and say, I know I equals E divided by R. 120 divided by 24, 5 amps. I know that. That's easy. Okay. And I know pi, 5 amps times 120 volts, 600 watts. Done. I can do that in my head faster than I can do V squared R. So I don't remember any of those other formulas. Never have bothered to.
And you could do that for any of the appliances in your house, right? In other
Yep.
words, the appliances are rated at like 1200 watts, like a stove. And you factor in, use the 120 volts, you can actually figure out how many amps that thing's gonna draw when it's powered up using, that's a practical use. Hey,
Yep.
Al, when you did your solar system, did you have to do any kind of capacity calculations or anything on that when you sized that thing?
Yes, I just, I took a totally different approach. But I pretty much added up because what I didn't want to do was spend the rest of my life camping. So I figured out what I needed to do to use high efficiency electrical appliances. So we had just normal everything and what it would take to power it. So I designed everything to be around high efficiency, which is something I guess a lot of people should take note of, because you just can't take a house that was built in 1950 and think you're going to turn it into a solar magnificent thing, because it wasn't built like that. We built ours to work off low power.
Right.
Okay, so you
And
the specs that they gave you. In other words, they said for the panel, it had so many amps or so many watts of power or whatever, and just added up what was there, right?
well, I pretty much added up what it was going to take to run the house. But what I also was of the opinion of, because I built a lot of houses, and it's like nothing, everything in the house isn't on at once. So when I put everything that I'm using, and I get, like a refrigerator, I got a Frigidaire Professional double refrigerator. It's 40 square feet. The thing's 6 feet across, you know what I mean? But it's super high efficient. But my house, when I have most everything on that you'd normally have on at the same time, my whole house basically it pulls like 17 amps.
Mm,
So yeah, so they when I did it, I kind of like put the panels together, the windmill, what it was going to do, and the diesel generator to pick up the slack, what I had to store for the battery bank. So I get a battery bank that stores 60,000 watts. It's like 2,500 amp hours,
mhm.
and it runs at 24 volts. And when the windmill is cranking, you can't use all the power. You just can't do it. It just generates so much, but that's not a constant. And then the sun around here, we only get about 6 hours a day that's any good for generating power. So there's a lot involved with the storage and the batteries and the diesel generator. You're not getting into an off-grid situation like I have without a fuel bill. Just isn't happening.
Yeah, like I said, I don't want to divert us too far, but all this stuff that Tom is going over is very applicable to kind of sizing and working the capacity and everything.
Yeah. Well, that's that whole thing with solar and wind power. I think that they're selling a. It ain't true what they're trying to sell. You can't have an off-grid house and turn on an electric stove or an oven and think you're gonna take every ounce of energy the sun generated in 6 hours and drain it before you're done making toast.
Yeah. All right. Well, and Al, it would be an interesting exercise, literally, EIRPIE, EarPie. You can go through your whole system and calculate everything, and it'd be an interesting exercise, especially where you're familiar with it, for you to get, no pun intended, grounded in these formulas. Okay. And Paul, I would encourage you to do the same. Find something around your house that you use commonly and apply these formulas to it. And if you think you got it right, great. And if you don't, bring it up to us and we'll walk through it with you. We'll look at common appliances, whatever you think is going to help you understand this. Okay. So we're going to move on. What's that?
No, I was just saying, it's like I did the whole thing. You guys were asking earlier on that, and I really didn't use a formula. I just went and I added everything up. I'm sure there is a formula. I didn't use one.
Right.
I'm sitting here like, I've spent my whole life like E equals MC squared, man. What's this E equals IR? So I was like, no, another angle. you know?
And that's why I keep it simple. Like I say, even as an engineer, I don't remember all those formulas. I remember the basics and work it out. And I've gotten fast enough at it that by the time someone else has done V squared R, I've done the other two formulas.
Yeah, but 120 squared, that's like 14,400, right?
Yeah. Yep. So, yep. So we're going to talk about series and parallel circuits because that's where this starts to come together and where you start to get an understanding. And being a pilot, an aviation enthusiast and a simulator pilot, I always look at the simple view, Bernoulli's law. And no, we're not going to look at that. We're not going to look at that at all. Airplane wing. Anybody understand how a plane flies? There's a heated debate among physicists and aviation specialists and aero engineers about this. When you pass air over a wing, the wing is flat on the bottom, in effect, and curved on the top. That means the air is all past, the wing's going through space at the same speed. The curved surface is going the same speed as the flat surface, which means when the air flows over this thing, the air flowing over the bottom, if you have, let me go back. If you have a spot of air at the front and it goes to the back, you have a molecule of air at the top and it goes to the back, they're both flowing, the wings move in the same speed. So what happens is the faster air on top has a lower pressure. Bernoulli's the one who figured that out, and he used all that fancy math up here to do that. And so we're going to ignore the math because that's what we do here. And it's lower pressure on the top and higher pressure on the bottom. So the debate, and I've seen aerospace engineers and no kidding, rocket scientists, everybody debate this. And I really don't know the true answer because every time I bring it up, it's like the Ford Chevy argument. Does the plane get pushed up into the air by the high pressure or sucked up into the air by the low pressure? It's a great debate, and I've seen it go on and on and on. And I've seen YouTube videos where it's disputed and solved and proven, and they all contradict each other. So go figure. But the reason I bring this up, okay, is this next illustration. Remember, I represented a resistor as a constriction in the pipe. You squeeze the pipe, you squeeze the garden hose. That's a resistor, okay? And increased flow, decreased internal pressure. That's the big thing, decreased internal pressure. So if I put a pressure gauge here in the pipe and I put a pressure gauge here in the pipe, I'm going to have lower pressure, okay? There is a difference in pressure here. That becomes important to our illustration because a similar concept happens in an electric circuit, okay? So here's my basic series circuit. I have a 12-volt battery, and I have 3 resistors in a series circuit, okay? If I equate this to a water pipe, this is what I get. I've got a water pump, and I've got 3 constrictions in the pipe. Those are my 3 resistors. So if we go back and look, just to be sure everyone gets it, we go back, we've got 3 resistors and a power source, the battery. Now we've got a water pump in place of the battery, and we squeeze the pipe narrow in 3 places, 3 constrictions, okay? So now we're going to think in terms of water flow. We've got 20 gallons per minute flowing through this pipe, okay? Now, think about a garden hose full of water, and think about pushing a gallon of water into the end of the garden hose you're at. What's going to come out the other end? If you put 1 gallon in this end, what's coming out the other end, Paul?
1 gallon.
Bingo. Okay, so what's my flow rate right here in the pipe? If it's 20 gallons per minute at the pump, what's the flow rate at the bottom of the pipe right here? Al?
I'm sorry, I get distracted. I got an old dog sitting next to me. He's having an issue.
So I got a pump pushing 20 gallons per minute out in the pipe right here. Now I measure it down here. How many gallons per minute are going through the pipe right there?
20.
Right? How many gallons right there, Paul?
I'd say 20.
Yep. And there?
It's still 20.
Yep. And so now this is important because if we go back to our electric circuit, we're going to think about current, flow rate, how fast current flows through the circuit, what the flows, the amps through the circuit are, okay? Now let's talk about our constrictions in the pipe. So I've got 30 pounds of pressure at the beginning on the pump, okay? And I measure it right there. If I measure across that pump, I'm going to measure that 30 PSI. Right there. This one's where people get a little bit turned around, okay? If I measure it at this constriction, remember that Bernoulli's principle thing. I'm going to measure a difference in pressure across there. When I constrict the pipe, the water flows through the constriction faster, I get a lower pressure. So if I measure across there, I'm going to measure a force, a pressure difference. That's electromotive force or voltage, just like constricting a pipe. Okay, same here. And the same here. Now, if I have the same size constriction at each point in the pipe, at these 3 points, am I going to measure the same pressure drop across them?
Yeah,
Right? And believe it or not, if I measure across them, I'm going to have a 10 PSI drop here, a 10 PSI drop here, a 10 PSI drop here, totals up to 30 PSI. Okay, that's how it's going to work in a water pipe. So let's go back to our circuit now and look at the electric circuit. Okay, so here's my circuit again. Think of this battery just like the water pump. These are the constrictions in the pipe. I made them all equal value. So if you're going to go down, Paul, where are you from? You're in 3 land? K38? Okay.
I
Got
mean, I'm
any-
in Florida. I'm in Florida. You talking to me, Paul Parker? I'm in.
Yeah,
Maryland.
Paul.
I'm in Florida.
Okay. So I've got a good analogy for Al up here, but I don't know one down your way. But if you've ever been into a rock quarry or chasm where you got to squeeze through the rocks, it
Yeah.
doesn't matter. You go down there, you eat your lunch and you head down there, you squeeze between a couple of rocks. It takes a certain amount of force to get you through there, especially if you're round like I am. Okay. And the more places you got to squeeze through, the more energy you burn, the tireder you get, right? The resistance adds up. Okay. Al would know this from places like Purgatory Chasm up our way. I just don't have a good analogy for you down in Florida. But the more places you got to squeeze through, the more resistance, the more energy you burn up. So resistance is in a series circuit adds up. Okay. So if we take this and now we're going to go through the characteristics of this circuit, and then we're going to talk about it. So if I measure with my good old ohm meter, my voltmeter rather, right here, I'm going to measure how many volts. If you take the meter and put it across your 12-volt battery in your car, what do you measure?
You're measuring the volt.
You're gonna measure the voltage of the battery.
From one side of the battery to the other.
Right,
12 volts, right?
12 volts. So now what happens if I measure here?
You can still get 12 volts. No. Wait a minute. So let's
No.
resistance is 10. So you got 10. The voltage is 10 and the ohm. So that's R. I'm trying to get this formula in my head.
Yep, that's all right.
Ohms. That's the
We're going to measure all 3 places, okay?
resistance, and we had a voltage. So 10. What's getting me right now is that are
Yep.
the 3 resistors added, or only the total circuit has 30 ohms, and
Yep.
just across where the point where you are right now, is that just 10 ohms of resistance?
Just 10 ohms right there.
Okay, so that'd be 10 divided. Okay.
All right, let's go through the math because you're headed in the right direction. You are absolutely headed in the right direction. So let's walk through this and look at what happens in this circuit, okay? So if oh, by the way, current. We'll do current first. Just like the water flow in our pipe. This one should be easier for you. Remember when we talked about the 30 gallons per minute, no matter where we measured in our pipe? If I've got this circuit, how much of the total current in the circuit, how much am I going to measure at each of these points? Think about our water pipe again. So if I break into the circuit here versus here, am I going to measure any difference? If I push a gallon of water through that pipe in 30 seconds, am I going to get a gallon of water in 30 seconds here and a gallon of water in 30 seconds here? Current, am I going to get 1 amp here and 1 amp here?
Yep.
Yep. So current through a series circuit is constant all the way around the circuit. Because if you push a gallon of water in the pipe at one end, you're getting a gallon of water out the pipe at the other end. Doesn't change. Okay. Pressure is what changes. So when we go back here and we've got 12 volts of pressure. Well, let me go the other way. There we go. We've got 12 volts of pressure here, and we got 3 equal value constrictions here. How much energy are you going to use getting through those constrictions? You're going to use 50% of it here. You're going to use, what are you going to use, do you think, where they're equal values? Making sense yet, or do you want to go through the math and prove it?
No, it's making this so it's so you say that again. What you said? What are we going to use?
Yeah, in other words, you're measuring 12 volts across that battery because there's a difference across the battery of 12 volts. There's a difference in potential of 12
Right.
volts. You got all those electrons built up on one side waiting to go racing, and they're missing on the other side. So you're measuring a difference in potential on that battery of 12 volts. Now, as you go through here, keep in mind that Bernoulli's principle idea that constriction causes a difference in pressure or voltage. So you're going to measure a difference in voltage across each of those constriction points.
Right, but it's
Question.
just at those constriction points right there.
Yep. Because if I measure across a piece of wire that theoretically has 0 ohms of resistance, and we can prove this with the math, I'm not going to see any difference in voltage. It's going to look like 0 volts. Okay.
So the statement that says the statement that well, I'm thinking you finally straightened out my head is the statement that I always hear is that the circuit has 30 ohm in a series circuit. That's right now is 30 ohms of resistance.
Right.
That has no effect on the overall circuit as 30 ohms. It's just that each point that you measure the resistance at is the effect on the pressure.
All right. So let's walk through the math because, like I said, you're chomping on the right idea here. So let me get past my current measurements here, and we'll go to the math. So the very first thing is, in a series circuit, the resistance adds up. It's just like squeezing through all those constrictions, or getting through all the traffic jams. You burn up a lot of energy in each one. So your resistance is additive. Your R total equals R1 plus R2 plus 3. So what's the total resistance in this circuit?
30 ohms.
30 ohms, okay? Now, what's the total current in this circuit? If it's 30 ohms, how many volts is it?
Wow.
Somebody break out the button box and tell me.
Voltage divided by resistance. 30 divided by 12. 12 divided by 30.
Yeah.
1 point. That's what I was getting ready to do. I would definitely need a calculator.
Yep.
Like 4 or something.
0.4 amps. Okay. 0.4 amps. Now that's through the whole circuit. Now remember our water pipes was the flow, because amps is your flow rate. So is it, right here, right here, right here, right here. It's 0.4 amps all over the circuit, right? Now, let's go on and talk about this. Now we're going to talk about just this one resistor right here. If I measure the voltage back here, we know it's going to be 12 volts. We got a 12 volt battery. We measure across it, it's 12 volts. So that's how I know 12 volts divided by 30 ohms, 0.4 amps. Now let's talk about this back here. If I measure across this resistor, I've only got how many ohms?
10.
All right, so E equals I times R. We know the current is the same. We've all agreed on that, correct? No matter where you go, the current flow is the same. So your I is 0.4, correct?
Right.
What's your R?
10 ohms.
What's your voltage?
12. 4 divided by, voltage is
0.4 divided by
We're just
rather.
looking at that one resistor. So
just
it's
the one resistor.
right.
You're not measuring the 30 ohms. You're only measuring across here. You put your meter right across these 2 points here.
Oh, okay.
And you're going to get 4 volts because it's 10 ohms. So 0.4 amps times 10 ohms, 4 volts.
Gotcha.
Okay. Now, coincidentally, the math is the same because I made all the resistor values the same. So you're going to have 4 volts here across this resistor, 4 volts here across this resistor, 4 volts here across this resistor.
3 times 4 is 12.
12 volts. Now you've tripped on a very, 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 very important concept. no matter what this set of resistors are, guess what the total voltage drop is going to be? 12 volts. So if I put a 10 ohm resistor here, and I put a 20 ohm resistor here, and I put a 30 ohm resistor here, the voltage drop is going to be bigger across which one? 10, 20, 30. Think of the math. So if I have 30 ohms here, we know the current's the same, right? So
The voltage is gonna be higher on the 30 ohm.
bingo, you got it. Now, let's make it easy. I'm going to make this 10 ohm resistor, a 10 ohm resistor, and a 20 ohm resistor. So now I have 10 ohm, 10 ohm, 20 ohm. What's my voltage drop going to be across the 10 ohms,
Same.
right? Current's going to be different though. So this is where it gets tricky.
Right,
Because
you gotta recalculate the current because the total of the three resistors is different now.
Oh,
right.
gotcha.
So it's E divided by R, but E is 12 volts. R is now 40 ohms,
40 ohms.
right? But I can guarantee you 10, 10, and 20, I don't even have to think about it. And as you grasp the concept, you'll understand this. I know 50% of my resistance is right there. So guess how much of my voltage drops right there? 50% of my voltage. 6 volts, 3 volts, 3 volts. If you do the math, you'll prove that out. So it's proportionate. It's going to consume all that pressure, just like you're pumping water would, but it does it across these resistors proportionately. So in the end, we've got a circuit now. Now, here's the next one we're going to talk about. Power. Think about a traffic jam. This is a constriction. We use the water pipe. If I constrict traffic by cutting lanes out for road work, how happy are the drivers?
Not too happy,
You could say they get pretty heated. True?
right?
Well, guess what happens in a resistor? It gets heated. Because you can't make energy disappear. It has to go somewhere. So when you constrict this flow and you reduce, you get that pressure in there and you get that drop in voltage, that energy has to go somewhere. Some of it goes away as heat. So we rate the power going through a resistor so that we can design the resistor to take the heat. Okay, so P equals I times E. Remember our calculated voltage up there? It's right above it, 4 volts. Remember our calculated current all the way through is what? 0.4 amps, correct? You following, Al?
I just had to run to the can, man.
Okay, so we've got our circuit. We've got our 0.4 amps running all the way through it. No constriction in flow. I didn't go there. So anyway,
I almost pissed my pants. I'm sorry.
0.4 amps all the way through. Okay, no matter where you go, 0.4 amps. We've all agreed on that. Grab that principle and hold on to it for series circuit. But here we've said we've only got 4 volts of the total right here. So how much power dissipation is going on right here? What's the power flowing through this 10 ohm resistor? P equals what?
The amps
And the amps is what?
was, yeah, 0.4,
And the E is what?
the
Voltage.
volts.
4 volts. So 1.6 watts. Okay. Now, if I go over this side, what's the current flowing through the circuit?
Oh, 0.4
4 amps. No
4.
matter where you go, it's the same. What's the voltage at this point in the circuit?
12 volts.
So what's the wattage?
That's 12 volts. Oh man, I understand what you're saying. I'm trying to do the math in my head and it doesn't work.
That's all right. That's all right. I note to self, tell everybody to have a real basic calculator handy. So I will do that for the next time. 4.8 watts. Okay. And again, 1.6, 1.6, 1.6, it just works. That's the beauty of the circuit. No matter what you calculate, it's all going to add up. Okay. And that, again, is how a basic series circuit works. Now we're going to get a little weird. Parallel circuits. Okay. We're going to use the water pipes again, but they behave a little differently this time. So now we have 10 ohms here, 10 ohms here, 10 ohms here, 12 volts. So all we did was rearrange our 10 ohm resistors into a parallel circuit, right? Simple, easy as pie. Ha. Here it is. Here's our water pump again. And we have our constrictions in the circuit here, okay? Now we got to think about what happens when we put 3 of those squeezed pipes in a row. We hook 3 garden hoses together. So you got to think a little bit differently here.
Mhm.
So we're going to talk about the pressure first, because this is a little easier to think about. Paul Parker, you had commented earlier about or asked about measuring across the wire. And I talked about there being, when you measure across the wire, in theory, there's no resistance here, therefore the potential is the same.
Right.
Okay. Keep that in mind when we look at this. I got 20 PSI at the pump here, right? What's my pressure right here,
20.
right? What's my pressure right there?
It's still 20 because
Yep. Bingo, you got it. Al, still 20?
Yeah, well,
Okay. Voltage, pressure, electromotive force. Keep those together in your head, because a parallel circuit does the exact same thing. Now, we're going to go to the slightly more complicated side of the parallel circuit. I got 30 gallons per minute flowing out that pipe right here, okay? So what's my flow rate right there?
30 gallons.
30 gallons. Now, what happens when we do this? What's the flow rate there versus there?
It's still 30 gallons.
But if I've got 30 gallons going down the pipe here, I just had to divvy that 30 gallons up, didn't I?
You have to divide it. Ah,
Right. So current or flow, amperes or gallons per minute, divide up here, okay?
but that's just for current.
That's just for current.
That's not my P. That's not my pressure.
Correct. Your pressure stays the same.
Gotcha. Okay.
You squeeze that thing and the pressure's gonna go all over the place equal, okay? So now, let's just say these are 3 equal constrictions or 3 equal resistor values, which you saw in the circuit. Those resistors were all 10 ohms. Can you get a grasp on what percentage of the flow is going up this pipe going versus going down this pipe?
you see, that's what gets me,
Okay.
right? So I look at this, well, you want to relate it to water.
Mhm.
I look at, I kind of, we have radiant heat in the floor of our house.
Yep.
Right, so it's all balanced through the manifold, and as you travel further, like the first restriction, so to speak, would have to be the greatest, because you'd have to, without having a restriction at that first pipe, it would all just flow right past it to the last pipe. So you gotta back things up in order. So how do you do that with electricity?
Think of these like valves that you close down to a certain level, because your manifold in your radiant heat, and that's what it is. It's a set of adjustable constrictions. And you get it, you adjust them so that the same amount of water flows through each branch of your radiant heat circuit.
Right,
You
the
got
left to its own, it don't do that.
Right. But this has those constrictions in it. Paul, you were saying something?
okay. The 30 gallons represents current, correct?
Correct. 30, it's not
Okay,
30
so-
gallons. Think about, hold on for one second. It's not 30 gallons, it's 30 gallons per minute.
Per minute, right?
Very important.
Okay. Now, so at the restriction points, you have 3 restriction points. The current is the same until it meets it hits its first restriction point, but you still have current flowing through the next.
Yep.
The same current is gonna.
So if I have 30 gallons, I put 30 ping pong balls in the pipe and push them down here
Right.
in 1 minute. Are all 30 ping pong balls going over here?
No,
Or are
because
some of them
are
going up
gonna
here?
go up there. Some, it depends on the restriction because some are gonna go up to. Now here's what I'm trying to get straight in my head. I'm thinking too much because current right there. Say all three resistors or the restrictions were the same. How
I
does,
think what's confusing, Tom, is that the three parallel legs are
Yep.
offset. If you drew this such that when it got to the first, the first Y in the pipe, if
Yep.
it was a three-way Y as opposed to successive Y,
Gotcha.
that
Thank
might be
you.
a little clearer.
Thank you. I think I'll try that. So,
now, okay, so you're saying right now, but see, I like the drawing. I mean, it's just that I'm seeing if I see ping pong balls going up, how does the ping pong balls? This sounds
Hey,
like-
imagine that the three legs all come into a three-legged Y in the pipe at the same point. What would you expect the ping pong balls to do? Divide equally among the three pipes, right?
Yeah, see, but I'm thinking too much because I see I see that, but I'm thinking, well, how do the ping pong balls know to divide equally? Let's see, but I understand.
It's random.
it's random, but they happen to divvy up because as many can fit through the constriction as at a time go through. But if they're three equal constrictions, the same amount go through. So it divides up evenly. So even when I get to this branch, I get the same action happening. Okay.
Right, gotcha.
So if I go back and look at this again, and by the way, ping pong balls is a new one. I haven't used that before, so I'm going to do that. So if I back this up, okay, we talk about these two. Whoa, go back. There we go. So I got 30 ping pong balls here. I hit this. Some of those ping pong balls are going up that way. The rest are going that way. So it happens that I've got one constriction here versus two downstream. About a third of them are going up the first pipe.
Right.
And 2/3 are going to continue on down the line. And about a third of them are going up that pipe, which only leaves a third to go up
The next
that
pipe.
pipe.
So you'd
Okay.
balance that with all different resistance sizing, correct?
If these legs of pipe were different sizes or different lengths, it would be different resistors. But if they're all exactly the same, then it would be the same resistor value. It's just the way the manifold works in your heating system.
Right? They should
Okay.
divide equally, right?
Yep. So let's do the math on this. First of all, resistors. Here's a concept for you. Remember in our other circuit, all three resistors added up. 3 10-ohm resistors became 30 ohms, right?
Right.
Now I have 3 resistors in parallel. What's going to happen? Do they add up? Do they divide? Do they multiply? What do you think they're going to do?
They're going to divide because each leg is.
Sort of. Watch this. And think of these like doorways, okay? You got crowds going down the hallway, and you've got a 30-inch door in one hallway and a 30-inch door in the other hallway and a 30-inch door in the other hallway. A third of the crowd's going through each door, right? So I take one doorway and I take it out here. And now I'm going to put the two doorways together. What happens to the total resistance of those doorways? It goes down. More people can fit through that doorway, true?
Right.
Because I just took two 30-inch doorways and put them together. So what happens when I add the third one into this? It gets even bigger. So what's the constriction or resistance here versus any one of these three? Is it more, there's less resistance here, true? More, it's easier to get through this doorway than it is to get through any of these three, right?
Yes.
So the total resistance in a parallel circuit is lower than any one of the resistors.
Almost like thinking backwards.
Yeah, it's a little bit of a mind bender, but if you think about it in
Mhm.
terms of passages and you put more passages together, it's easier to get through. It's a bigger passage.
So
Okay.
if you want to build a circuit, if you wanted to allow more current to flow between those, each one of those pipes or channels or whatever,
Yeah,
you put them in parallel.
yeah. So let's now go back to our circuit. Now we have 3 10-ohm resistors. All right. The formula for this is a little weird, but we'll get to that in a minute. 12 volts here, right? Pressure across here.
Mm-hmm.
Voltage across here is
12 volts.
12 volts, 12 volts, right?
Mhm.
And 12 volts. Now we're going to get a little more interesting. What's the flow right there? Remember the ping pong balls or the water? Is it all of the flow, total flow right there?
Yes,
Yes,
Okay, so if I move the meter down and I measure there,
Be
not total
1/3.
flow, true?
Right, 1/3 of
1/3. And there,
same thing.
third.
and there.
2/3.
Now,
Now,
if
let me
I-
hold it
Yep.
before you go any further.
Yep.
The flow between the first two, is that 2/3? Or the
If
same?
I-
Well,
it's going to be about 1/3 in each. So the flow between these two right in here, you mean?
no, right between the next resistor on the next branch.
Right here?
No, behind it. Yeah, that right there.
It'll be about 1/3 because it's an
So-
equal resistance value.
So that wouldn't
Okay.
be 2/3.
Nope. It'd be 2/3 down here if I measured right here. Because you got 1/3 of the current going up this way, therefore 2/3 of it is headed this way. So if I measure right, if I broke my circuit right here, I'd measure about 2/3, okay? So if I measure up here, I'm gonna measure about 1/3, right? That's what's flowing through this leg. If I
Right.
break
I
the
got you.
circuit right here, I'm gonna measure about 2/3.
Okay, I got you. Okay.
And of course, if I break it right here, I'm going to measure 3/3, all of the current. Okay. So keep in mind that in a parallel circuit, it's your current that's different at different points in the circuit, but your voltage is the same. In a series circuit, it's the opposite. Your voltage drops across each resistor, but your current stays the same. Okay. So again, if we do the math on this circuit, this is the weird one. This is, I promise you, there aren't too many weird formulas like this, but that's how it works. Add the doors together and the passageways, and 10 ohm, 10 ohm, and 10 ohm becomes 3.333 ohms. Because it's wider and wider and wider, therefore there's lower and lower and lower resistance. Okay. So in my total circuit, I have 3.333 ohms and 12 volts, right? So if I take my current measurement right here, I equals E divided by R, I'm going to come up with 3.6 amps because I have 12 volts divided by 3.333 ohms, right? What if I measure it right there?
We already said that's going to be
1.2, 1/3 of it,
right.
because it's E of 12 volts divided by an R of 10 ohms. And if I measure it up there, it's going to be 2.4. Remember, it's 2/3 of it. So the math backs up the plumbing and the highway and the ping pong ball example perfectly.
The math backs up the plumbing.
I did a funny.
Didn't even mean it.
So power, keep in mind, each of these dissipates a certain amount of power, or right? So P equals I times E. So what's our E going to be right here? What did we say in parallel? The voltage is what? The same or different?
Same.
Same. So you got 12 volts times how much current in this one leg?
1.2.
1.2.
Right.
14.4 watts. So if I measure it over here,
We're already. Oh,
what's my I now over here?
it's 3.6.
3.6. What's my E over here?
12 volts.
43.2 watts. It all adds up perfectly. That's if you test it, if you do the math on a circuit, it's all going to add up. And if it doesn't, go check your math. Because you got one of them wrong, because it all adds up. Ask Kirchhoff for any engineers in the group. So that's what we've gone over. Believe it or not, that's the basics. Now, we did move at a faster clip than I wanted to, and I apologize because I'm working my way through this course. But that's the basics we went through. Okay. So we talked about what electricity is, how it flows, where it flows. We talked about how do you measure it, voltage, current, resistance, and ultimately power or wattage. And we talked about series and parallel circuits. So first of all, I appreciate the two of you in particular coming in here. I'm going to ask the instructors for their critiques as well, because I want to reshape this course and fine tune it till we get it to where it's accomplishes that end goal of helping someone with no technical background get through it. So whether you're willing to comment live on screen right now, or whether you want to shoot me an email with your critiques and comments, I'd appreciate them. Good, bad, or otherwise, let me know about the pacing. Let me know if the examples made sense to you, or if there are other examples. I took notes on things like Bill's idea and Paul's ideas about how to show some of this. And I was watching how each of you were consuming this content. So I'm very interested to know what your thoughts are. Okay.
I enjoyed it, and I found it easy to follow. It made me think too much about the theory. I got to the theory. My brain started going into the theory, which, over the years, and then I'm like, but now it cleared it up, because, you cleared it up. The examples.
So I was going to comment, Tom, I don't know if you want to stop the recording at this point. This is what you wanted to cover tonight, right?
Yes, it is.
Okay.
I got a few bonus slides, but I'll wait till we're done for those.
All right. So I don't know if Ray is still on or wants to stop the recording or not on it.
I want to pick up some good rumors.
I was gonna.
Get some dirt. No.
So do you want my critique online, or do you want it here?
I'm fine either way. Whatever you want to do. I mean, I'll take it either way. Like I say, I'm just as interested in Paul and Al's comments as I am the other instructors, because I want to shape
And
this
actually,
course.
I would want their critique of my critique.
Okay, I am going to stop the recording now.
Now let's stop that.